we are going to be doing hypothesis testing part 2. As if part 1 wasn't enough, we definitely want to, expand on this because I know you guys love this topic. So do I. Maybe there's a part 3. Just kidding. There's definitely not. But you know what? We love hypothesis testing. So, oh look, I even put it would be on September 20th, but it's not. It's the 27th, but it's okay. All right. Let's talk. Okay, yeah, I did this last week. I just want to make sure that we're clear on the difference between confidence intervals and hypothesis tests. So remember, our confidence intervals are going to be a range of our values, while our hypothesis tests are going to be a single conclusion. So everything we're talking about today and that we talked about last week, that's when we make that single conclusion based upon if we reject or fail to reject our null, all that kind of stuff. So that's like the main difference. Remember, confidence intervals, we had that range between our lower bound and our upper bound. Hypothesis tests, we are just going to have a single conclusion at the end, and we're using data to basically decide against the hypotheses that we had. So let's do some more stuff with this. So, errors. This is not good. These are things we don't want to do, obviously. We all make mistakes. We are humans. But errors in statistics are no bueno, okay? So when we're talking about errors in our decision making, this means that after we made our decision, if we made a wrong decision, that's basically what we're talking about when we're talking about errors. So in this case, if we make a type 1 error, that means that we're going to reject that null hypothesis when in reality that null hypothesis was true. Okay, so that's us saying that we say that there's some sort of change going on, but really there was no change. So we made a mistake there. And remember that alpha level that we talked about last week that we often use as 0.05. That's the same thing as I was showing you, like the rejection region. It's the same idea there. Our alpha level is going to be the probability of making a type 1 error, because if you remember that alpha level of 5%, we use that for our 95% confidence intervals often. So in this case, that's gonna be like the percentage or the probability that we reject the null when it's actually true. And then on the other side, we do have a type 2 error, which is when we fail to reject the null when in reality the null is actually false. So we're saying that there's no change when in reality there is some sort of change going on. So we also call that beta. So beta is our probability of a type 2 error. And so yeah, it's just, and if you look at this table that I have down here, it's just showing you, so here is a type 1 error. If you read this like a two-way table, like a contingency table, we have like if we reject the null when in reality it's true, here's our type 1 error. And then for type 2, if you don't reject the null when it's actually false, then we're going to have a type 2 error here. We'll talk a little bit about power, just kind of put this over on the side so you're aware of it. But yeah, so just so you remember, alpha is our significance level and also our probability of a type 1 error in this case. Okay, so power, every semester people kind of get goofed up about this, so don't think about it too hard. If you remember, like we just talked about, beta is our probability of committing a type 2 error. So our power is basically everything but that. Okay, so 1 minus beta is our power. So remember, if our type 2 error is going to be our rejecting the null hypothesis, given that the null hypothesis is false. And then you're given as true, sorry. And then if we increase that sample size, then remember our standard error is going to decrease, which is good. Remember, we want less chance for error, which is also going to increase that difference between our sample statistic and the hypothesized value. So, and this last point I have here, so if you decrease alpha, you're going to increase your beta in this case. So the main thing you want to realize with this is that if you're decreasing the chance of making a type 1 error, then you are going to increase the chance of making a type 2 error. So that's the main thing to think about there. So yeah, power is just 1 minus beta, 1 minus the probability of committing a type 2 error. So yeah, power. All right, let's see. Okay, oh yay, p-values. So p-values are super fun. These are basically, that's what we use to discuss about our like our significance level. We're saying this is like how we make our conclusions based upon what our p-value is. And we take our p-value from what we got, and then we are going to compare that to our significance level. So yeah, this is just a little bit of a review. So when we make a significance level, so often we use 0.05, you'll see that very often. When we have that significance level, basically what we're saying is that we are accepting a 5% chance of making a type 1 error. Because remember, alpha is our probability of making a type 1 error. So if we make that significance level alpha, or if we make it 0.05, that's saying that we are okay with the fact that there's 5% chance that we can make a type 1 error. I mean, obviously that's 95% chance that we don't. So remember, type 1 error, rejecting the null hypothesis when the null hypothesis is true. So saying that there's a change when there's not. So yeah, and often people talk about, you know, when is a type 1 error more dangerous? When is a type 2 error more dangerous? It's not a set in stone thing. Like type 1 isn't always more dangerous, type 2 isn't always more dangerous. It's totally dependent on the context of the problem and the situation. So if you think about it, when well, and if a type 1 error is more dangerous, then you want to have a smaller alpha level, because you basically want to be accepting a smaller chance of making that type 1 error. So if you realize that a type 1 error is more dangerous, you're going to decrease that alpha level even more, so you decrease the probability of making that type 1 error. So yeah, that's often in medicine. If you're doing trials in medicine, a type 1 error can be more serious, because basically you would be rejecting rejecting the null when the null is actually true. So you can be saying that like a certain treatment is helping someone when it's actually not. So you're making that assumption that everything, you know, is going well when it's not. So that could be, you know, someone's health on the line. So that's where a type 1 error may be more dangerous, and you want to make sure this alpha level is lower, and then your p-value kind of has to be even smaller in order for it to be statistically significant in that case. Okay, publication bias. This is basically just talking about when you see something, this is like, you know, real world. If you see something in statistics like published that says that's something statistically significant, we do want to keep in mind that it's not always representative of actually what is statistically significant, because they're really only going to be publishing the good stuff, obviously. You know, if you did a bunch of trials and you know, only a few of them worked, you're gonna, you know, show those and be like, these were statistically significant, this is good. But, you know, little do you know, there might be a whole bunch of them that weren't statistically significant. I liken this to if you see the commercials where it's like 9 out of 10 doctors agree that you should eat carrots to be healthy. So like but the point being is that they could have interviewed like 100 doctors, and then maybe only 9 out of 100 did, but they're just going to tell you that 9 out of 10 of them did if they were to take 10 of them, and it just so happened that the 9 that said yes were part of that 10, you know. So the main thing is that, you know, if they do a bunch of studies and only a few are statistically significant, they're only going to publish those ones that were statistically significant because that looks good. They're not going to publish the ones that weren't, and little do we know, it could be, you know, the majority of the different tests that they did. So we don't really know that. So it's just something to keep in mind. I mean, obviously, good publications aren't going to do this, but it is something to keep in mind when you're looking at different statistical reports, to make sure that you understand that it isn't always what it seems. Okay, so more about statistical significance, just the fact that it's, the whole point of it is saying that it's the magnitude of the difference. It's like how much of a difference, excuse me, do we actually see? So we want and effect size is another way to say it because it's saying like how big is the effect on this. So the whole point, if something is statistically significant, we are saying that what we found has a difference large enough that it actually, means something. It's something that we can use in real life practically, and it'll be important. It's not just something that we just kind of found out by numbers. It's something that we found to be statistically significant, and it's big enough that we're like, okay, this is actually something we can use, and then that's when it's published and whatnot. So that's why it's important to choose your alpha levels wisely, because when you find that p-value, you want to make sure that you're comparing it to an alpha level that's going to give you accurate statistical significance. So that's why you don't want to have a large alpha level, because then you're giving a large probability, you're like accepting a large probability of making a type 1 error, and then if you do make one, you may not notice it because your p-value may be fitting into what that what your criteria was, but in reality it's not actually what it is. So keep that in mind. Okay. Reviews already. I feel like I'm talking so fast. I keep doing this. Well, okay. All right, let's do some reviews. Okay, so here's a hypothesis test for a population proportion below. So we have our null is that p equals 0.1, and then our alternative is that p is not equal to 0.1. So we have a two-tailed test here. So if our sample size is n equals 100 and the sample proportion is p hat equals 0.1, then what is our z-test statistic? So this is kind of to test, if you understand standardization and our z-curve. So go ahead and look through these and let me know what you think the answer is. Okay, good job, guys. All right, so let's where did my pen? Oh, there. All right, so let's look at this. So remember, I did not mean to put that little dot there. So remember, when we are trying to standardize something, we're trying to take what we got from our normal curve and like what we got from our different tests, and then standardize it to a z-curve. So I always like to think of it as normal curves like this, like on top of one another. Oh, that first one was so good, and I kind of goofed up there. But okay, so let's draw our first one. So if we were to have, it says that our population proportion P is given below. So our sample, or our mean in this original one, this is going to be what we actually got here. Our mean is going to be 0.10, okay? Because whatever is in our null and alternative hypothesis is going to be our mean, okay? So if you look at this, this is going to be our mean. This is technically 0 standard deviations away from the mean if you think about it. So now if we go down here to our standardized z-curve, remember our z-curve has a mean of 0 and a standard deviation of 1, okay? So in this case, we're trying to standardize this 0.10 to whatever value we got our p hat to our z-curve. So as you can see, the sample proportion that we actually got is the same thing as our mean. It's just 0.10. So we're trying to standardize that onto the normal curve. So if 0.10 is the same thing as our mean, our center, then in that case, it aligns with 0. So it's going to be B because it's going to align with, like, 0.10 is the mean. It's 0 standard deviations away from the mean. So then on our z-curve, it's also going to be 0 down here. Does that make sense why it would be B? I know this is a little tough. I know, I understand. But yeah. Is that good with everyone? Do you want me to go over it again? Yay! For now, I know, right? Okay, great. Let's go. All right. Oh, and I also, you can also do it this way. Look, I was all prepared. All right, so we can also look at it this way. So remember, if you actually wanted to solve it this way, I kind of showed you how to do it like visually. But if we go through this and think about the last problem, remember our p hat was equal to 0.1. Our p null was equal to 0.1, 0.10. This was all given in the last equation. And so that's all we need here, really. So if we were to actually just solve this, z equals 0.10, so p hat minus 0.10, which is our p, and then divided by, and you can go ahead and do all of this and like go through it, but honestly, like, you can just kind of remember our n. I don't remember what n was. SOS, let's go check. N was 100. So in reality, you could go ahead and write out this denominator like I did, but 0.10 minus 0.10 is going to be 0, and 0 divided by anything is going to end up being 0. So that's another way. You can figure it out with this equation too, if that last way that I did it was confusing. But some people like it with the picture, some people like it with the equation. So I think it is important, though, that, most people can do this equation and get the answer, but I think it's important to also understand the concept of how we're standardizing that, how the fact that 0.10 was aligned with our mean, so then when we standardize that to our curve where the mean is 0 and the standard deviation is 1, that's going to standardize also to our mean of 0. That's why it's 0. So the other way I explain it is kind of conceptual. This one's more just plug and chug. Chug, chug, choo, choo. All right. Yay. All right, number 2. Let's try this. Okay, so given that the alternative hypothesis is really true, probability that the null hypothesis will be rejected is known as what? Go ahead and try this one. Yay! Good job, guys. Great job. So yeah, this answer is definitely A. This is basically the definition of what power is. So this is saying that our null is true. So we're looking at the probability that, or I'm sorry, the alternative is true. So we're looking at the probability that our null is rejected. So remember that all this is going to be our 1 minus beta. And remember that beta is our probability of a type 2 error. So good job, guys. You definitely understand that. I thought I heard a bug. Sorry. Okay, let's keep on cruising. Okay. Whew. Alrighty, so at one student-run cafe, the number of muffins sold. Ooh, muffins. The number of muffins sold each day was recorded for 47 days. Assume that a representative sample, given the output, which of the following conclusions is correct? So go ahead and look at this mini-tab output I gave you on the right, and check these answers and let me know what you think. Okay, great. Good job, guys. Okay, so let's need a new color. All right, so remember in this case, so we want to check out our p-value, and then we always just assume, and you can tell, so we're talking, 95% confidence interval, and then, so we're going to assume, remember that alpha is 0.05 if we're not given it. And so in this case, if we're comparing our p-value to our alpha, our p-value is going to end up being less than alpha because 0.1148, I'm sorry, wrong way around. Our p-value is greater than, it's greater than alpha. So we are going to end up rejecting or failing to reject our null since our p-value is greater than alpha. So since we're going to fail to reject that null hypothesis, we're saying that there's no evidence that the population is greater than 5. Because if our p-value is greater than alpha, we're going to fail to reject the null. And our null is saying that the number of muffins sold each day was 5, as these say. So since our p-value is greater, we're going to fail to reject this null, so we're going to still assume that's true. So we do not have evidence that the population mean is greater than 5 because we failed to reject that null, so our answer is D there. Does that make sense? Actually, I should probably say also that we say that the population, we want to make sure we say the population mean. That's why A isn't correct, because it said that in this sample. Because remember, the conclusion we always make is always about the population. So that's why D's correct and A isn't, because it's always about the population. So does that make sense to everybody? Yay! All right. Alrighty, let's do another one. Okay, a university administrator writes a report in which he states at least 45% of all students have driven under the influence of drugs or alcohol. Bad. Don't do it. Many others think the correct percent is less than 45%. What are the appropriate null and alternative hypotheses for the situation? So this is the practice writing null and alternative hypotheses. So let me know what you get. Yay, good job, guys. Absolutely. So our answer is C here. You guys definitely understand how to write hypotheses, which is good. That's very important. So remember, oh, that was a big circle. So remember, in our null and alternative, when we write hypotheses, we're always writing in terms of the population because our conclusion is always in terms of our population too. So A and B aren't going to be correct because that's writing with samples. So that's no bueno. We don't like that. So A and B can't be correct. So our answers that were between are C and D. So what we want to do is look at what basically what we think the change is. So it says many others think that the correct percentage is less than 45%. So it has to be almost it has to be Z. It has to be C because our alternative is the one saying less than 45%. D is saying not equal to. So if it said that many others think the correct percentage is not 45%, we'd use D. But in this case, it'll be C because we're talking about less than 45%. So good job. You guys did a great job with that one. All right. We have a few more. Ooh, okay. All right, which statement is correct about a p-value? So read through these answers and let me know what you think about them. Okay, let's go over this one. So remember, our p-value is talking about the probability of committing, or I'm sorry, our p-value is talking like the probability of like what we found being there or more extreme than that. So when we have a small p-value, that is going to provide stronger evidence that the results that we produced by the sample didn't occur by random chance. So we're saying that, so remember, when we have a p-value, here's another thing. When our p-value is less than our alpha, then we're going to reject the null. So we're saying that there's a change. Okay, and hope you can see that. There's a change in favor of the null. In favor of the alternative. So yeah, we're saying that there's some sort of change going on when we have a small p-value. So when we look at these, A says the smaller the p-value, the stronger evidence in favor of the alternative hypothesis. And this is actually going to be our correct answer, because if you look at what I just drew, if we have a small p-value, that means that we're going to reject our null. So rejecting our null is in favor of our alternative. So that's why small p-value, reject the null, favor of the alternative. So that's why it is A. B is not correct because the smaller p-value does not talk about stronger evidence in the null, because it's the other way around. So because we're saying if we have a small p-value, we're saying there's some sort of change. No, it's not. Don't worry. That's totally, this is a tough concept to wrap your head around. It's just stuff that, you know, the more practice you get, the more it makes sense. But so yeah, small p-value, reject our null, and then yeah, I understand that's a very common mistake. So yeah, and that's gonna be in favor of the alternative. And then C and D aren't correct because they're talking about like whether or not they are, and it does depend. So does A make sense to everybody? Yay! Raise the roof. All right, cool. Alrighty, let's see what we got next. Yeah, and sometimes you know it makes more sense to me after my explanation. I hope it helps. Don't ever tell me it makes sense if it doesn't make sense to you guys. I'm more than happy to explain it again. You know, this is for you guys. This isn't for me. So, but okay, let's do a few more. So, a hypothesis test is done in which the alternative hypothesis states that more than 10% of a population is left-handed. P-value for the test is calculated to be 0.25. Which statement is correct? So read through these. Let me know what you think. Alrighty, let's go over this one. So, good job. Our answer is D in this case. So, if we look at this, our p-value is 0.25, okay, and that's very large in comparison to our significance level. So, in this case, it is greater than our alpha, so we're going to fail to reject the null. So if we fail to reject the null, that means that we're still going to assume at this point that the null is true and that there's no change going on. So in this case, we cannot conclude that more than 10% of the population is left-handed because we're going to assume that the null is still true, saying that 10% is left-handed, because our null would be that p is equal to 0.1, and then our alternative would be that p is more than 0.1. So in this case, we failed to reject the null, so we're still going to assume that it's true. So we can't make any conclusions that the alternative is correct. So that's why D is the answer in this case. We are in favor of the alternative hypothesis. So does that make sense to everyone? Yes, good job. You guys did a great job. This is D. Anyone have any questions about this one? I'll take that as a no. All right. I think we have one more. Oops. All right, let's do another one. Okay, a team of medical researchers was examining the effectiveness of asthma treatments. They were comparing two treatments, old and new, and rejected the null hypothesis, concluding that their new treatment was superior. So which of the following is not a possibility in this case? So try this last one and we will go over it. Okay, good job, guys. So if we look at this one, if we reject our null hypothesis, so if HO is rejected, then we have two options for what could have happened here. So either our first option is that we made a correct decision, okay? And then our other option here is going to be a type 1 error, okay? Because remember, a type 1 error is when we reject the null when the null is actually true. So these are our two options that could happen if we reject our null. So in this case, we can't, it's not possible to make a type 2 error, because if the null is rejected, these are our two different possibilities. A type 2 error is only occurring if a false null hypothesis is not rejected. So in this case, we did reject the null, and a type 2 error would happen if we initially had failed to reject the null. So in this case, we can't have a type 2 error because we initially rejected the null. So our answer is A. We cannot have a type 2 error. Does that make sense? Yes, I try to put the not in all caps. I'll put some stars around it next time. Wee. Not. Put a little dude in here. Doot, doot, doot. Okay. Good job, guys. Alrighty. Doot-a-loop. Alright, so that's all we got for tonight. If you haven't already given me your email in the chat box, you can go ahead and type that in for me now. We'll have our next group review on Sunday, and then we'll have more information about the midterm review that I'll do that week. Our schedule will be a little bit different, just to make sure that we have enough review for you guys in Q&A. So we'll go ahead and do that. So if you have any other questions for me, go ahead and type them in the chat box. If not, you are good for tonight.